This is problem 28 from the electric potential section. A region of space is filled with the electric potential illustrated below. The equal potential lines are separated by 10 volts. So this one is labeled as 80, so it would go, and this one is 40, so it's going down. So it's 80, 70, 60, 50, 40. A proton is at rest at each of the points A through F. We want to rank these protons on the basis of the magnitude of the electric force acting on them. In the electric potential lab, we learned about the relationship between the electric force and the electric potential, and we learned that the electric force is equal to the negative gradient of the potential. However, we're not really going to be using this equation this way in this class because you may not have learned about the gradient yet. And so instead of using the equation this way, we're going to say the radial component of the electric field is equal to the negative derivative of the potential with respect to r. It's really supposed to be a partial derivative. However, in this course, it doesn't really matter whether it's a partial derivative or not. So I'm going to write it as a partial derivative, but you can take an ordinary derivative, and in this class it's not really going to make a difference. It's very interesting that you can take the potential, which is a scalar quantity, and from that you can get the electric field, which is a vector quantity. So you can do that for the radial component, and you can also say the x component of the electric field is equal to the negative derivative of the potential with respect to x. Same thing for y and z. And negative derivative. There we go. But this one is going to be what we're sticking with for now. Since I happen to have one of my favorite electrodynamics textbooks handy, you may be interested in knowing that if we take the gradient using Cartesian coordinates, so x, y, and z, we just take the partial derivative. Here you can see that is a partial derivative and not an ordinary derivative. If they're not taking the gradient of of v, they're just taking the gradient of t. So yeah, it looks a little different than what we have here, but this is how you would do it in Cartesian coordinates. In spherical coordinates, however, it gets a little bit more interesting. So if you are going to use this formula in spherical coordinates, this much is true. So when you take the derivative with respect to r, that gives you the radial component. The polar and azimuthal components are more complicated to find, but fortunately for us, we're only interested in the radial component of the electric field. So that's what we have here. Okay, so what do we need to learn from this? Well, also in the electric potential lab, we said that if the potential doesn't change very much, the electric field is approximately equal to the change in potential over the change in distance. You can see that from the equation that we have here. The slope would be the change in potential over the change in position. And that's approximately equal to what we have here as long as the potential isn't changing very rapidly. Okay, so basically, if I look at my diagram here, the field is going to be stronger when the potential lines are closer together. So as I go from one line to the next, the change is always going to be equal to 10. So let's say the numerator is always equal to 10, but when the lines are closer together, the denominator is going to be smaller, which means the whole quantity is going to be greater, which means the electric field is greater. So the electric field is stronger when the lines, the equal potential lines, are closer together. So that's what this equation here is telling us. So rank the protons on the basis of the magnitude of the electric force acting on them. Well, at A, the lines are very close together. So look at the distance between the two lines. At B, the distance is a little greater. At C, the distance is even greater. And then at D and E, you could go to either side. So like this or like this. That distance is going to be greater than what we have at C. And for F, the field lines are getting, the equal potential lines are getting further apart. So we have A, the field lines are closest together. The equal potential lines are closest together, so the field is strongest at A, and then B, and then C, E, and D are equal to each other. They're both, I think if you draw a horizontal line here, they're the same distance away from the horizontal, so they'd be symmetric. So D and E, and then at F, the equal potential lines are the farthest apart. In part B, we're going to rank the protons on the basis of the angle the electric force acting on them makes with the x-axis. Oh, well, I kind of skipped something here. We weren't ranking on the electric field, we were ranking on the electric force. Fortunately, know that the force is just equal to Q times the field, so since it's a proton in each case, the field is proportional to the force. So if I find the direction of the field here, it's going to be the same as the direction of the force because it's a positive charge. And in the electric potential lab, we should have learned that the force is always perpendicular to the equal potential lines. So perpendicular, and if I have a higher potential here, this type of potential would arise from having a positive charge here. So if I had a positive charge here, and then I put another positive charge here, the force would be acting away. And remember, the field points from higher potential to lower potential, and the field lines are perpendicular to the equal potential lines. So if I draw the field lines, they'd be perpendicular, perpendicular. There we go. So rank the protons on the basis of the angle. Well, C is going to be an angle of 0 degrees. And then F would be a slightly smaller angle than D, which hopefully you can see because the lines are perpendicular to the equal potential lines. Then A, and then B, and then E. So there's two important things that you should learn from this problem. The electric field is stronger when the lines are closer together. And, well, one, the field points towards lower potentials. Remember in lab we talked about if you picture the higher potentials as the top of the hill and you dump out a bucket of water, the field lines point in the direction that the water would flow in, so pointing towards lower potentials, and the field lines are perpendicular to the equal potential lines. And that's it for problem 28.